Hi friends, welcome back to LGF. So today we have to start the 11th lecture. Till now we completed, or in the last lecture we have seen the second order system transfer function. So let me start with the transfer function of the second order. Just wait. So for the second order system, the transfer function we have seen is omega n square divided by a square plus 2 zeta omega n s plus omega n square. Correct? This was the transfer function for the second order system. Okay. And where omega n is the natural frequency of oscillation. Okay, in radian per second. Correct? Okay, this zeta, and this zeta is nothing but the damping ratio. Correct? This is damping ratio. We are getting in comment that please provide the PDF also. Okay, we'll provide the PDF. Okay, don't worry about this. So this zeta is the damping ratio. Perfectly fine. Omega n is the natural frequency of oscillation. Okay, now what is the point? The point is, we have seen if you have the second order system, in the last video lecture only we have seen, if you are applying some input to it, you are getting some output from it. Correct? So the relation between input and output is affected by the third person, and that is zeta. Correct? We have seen the output of the second order system is totally depends on zeta value. Correct? Input and output relation is affected by zeta. So this is the kind of extramarital affair. The relation between these two people is going to affect by the third one. Right? So the same thing is here also in the second order. This zeta is controlling the output. Correct? We have seen for the different values of the zeta, for the second order system I'm talking about, if you are applying any input at the output, you will get oscillations. If your zeta is 0, you are getting continuous oscillation or natural oscillation or sustained oscillation at the output stage. Okay, these are the natural oscillations. Correct? When zeta is 0, this system we call the undamped system. Definitely, if you undamp the system, it will have natural oscillation. Okay, when zeta will be 0, you get this. Then we have seen what will happen when zeta will be in between 0 to 1, and we have seen one condition when zeta is less than 0. We have seen this condition also. When zeta is less than 0, the system was totally unstable system. Correct? So for the stable system, we have seen the zeta should be greater than 0. Sometime I call this zeta del, so I'm sorry about that. Okay, please understand. So when zeta will be greater than 0, the system will be stable. So if this is greater than 0 or equal to 0, the condition is starting from the 0, stable and marginally stable also, because at zeta equal to 0, the system is marginally stable. We call it marginally stable. That's why I'm taking it here greater and equal sign. Correct? So in this we have seen last time that it is underdamped system. This is underdamped, means now your system output will be damped by some factor, whatever value of zeta you are taking over here. Correct? In this case, we got the output like this. Damped oscillation means at t equal to infinity, it's going to die. Correct? This is damped oscillation. This is not natural or sustained oscillation. The oscillation will remain at t equal to infinity also. This is not like that. Okay? So it's like if you are suppressing some signal, definitely at the output you will get the suppressed output, or I can say it equal to infinity, you will get the 0 output. Then we have seen zeta equal to 1. This was the case of critical damped system. Correct? This was the case for the critical damped system, and in this critically damped system, the output will be like this. No oscillation will be there. There will be no oscillations. Then we have seen zeta is greater than 1. This was the case of overdamped system. This was the case of overdamped system, correct? And the output, if I'll draw for the overdamped system, it will be like this. Okay, soon it will be die out, correct? So we have seen these 4 conditions. Now let me come in the figure over here. This is the case when zeta was exactly equal to 0. We got the poles. If you remember, plus minus j omega n, we solved the equation in last video lecture. So here we are getting the oscillation when zeta is equal to 0. This is the case 1. Let me take this is case 1. Here is the case 2 over here. This was the case of underdamped system, in which we got the poles minus zeta omega n plus minus j omega n 1 minus zeta square. Okay. If you people are getting any difficulty, please you can switch to the control system 10. Please watch that session, so you'll get automatically how I got this one, correct? So this was the case 2. Here this was the case of underdamped system. The oscillation will die out at t equal to infinity. You'll get the 0. Okay. The case 3 over here. This is the case 3. In the case 3, we got the it was 2 times we get minus omega n minus omega n. These are the system poles. So here 2 times we are taking 8 minus omega n, correct? So this was the case of critically damped system. This was the case of critically damped system. And over here for overdamped system, we got 2 poles. One is near to the imaginary axis, one is away from the imaginary axis. So for this is case 1, this is case 2. For the case 3, we got repeated poles at minus omega n, perfectly fine. This was the case 3. I hope it's clear to you now. This is S, okay? This is not zeta. Number of poles we are talking about, so I'm taking just S. So in third case, in the fourth case, we got minus zeta omega n plus minus. Now it's not j, it's directly omega n. Over here, zeta square minus 1. Okay, we got this. So this is the so these are the poles over the negative real axis only. There is no imaginary part over here. This is the case 4. That's why we are getting one pole near to the imaginary axis, another pole is away from the imaginary axis. Now come to the conclusion. When zeta is going to increase, we have seen this limit that when zeta will be greater than 0, then only system will be stable system. Now we'll see this zeta is moving towards 1 from 0. Okay, let's take it. Suppose this zeta is moving. Wait a minute, let me change the pen so it will be clear to you. This zeta, at zeta equal to 0, our poles are over here. This is the case of marginally stable system. We have seen if zeta is 0, this is the marginally stable system. When zeta is greater than 0, it is the stable system. When zeta is less than 0, definitely you will get unstable system. Okay. Now the question is, or the point is, when zeta is moving towards 1, what will happen? The poles will see at zeta equal to 0, your poles exactly located on the imaginary axis. When your zeta is going to increase, here this is the case of zeta going to increase, correct? Zeta is going to increase. Here zeta value we are taking in between 0 to 1. Your poles are moving away from the imaginary axis, correct? zeta will move towards 1, your poles will move away from the imaginary axis. This side your poles will move perfectly fine. Wait a minute. So let me come over here. I'll discuss about the zeta values, but before that let me clear some points. We'll talk about the time constant. Correct? We have seen last time the time constant. Time constant is given by minus 1 divided by the real part. Correct? Real part of any pole over here. See, for if this zeta equal to 0, if we are talking about, it means for the marginally stable system we are talking about. For this we have seen, we got the S is nothing but this. We got this. Over here there is 0 real part. 0 plus minus zeta omega n. So if I'll calculate the time constant over here, it will be minus 1 divided by 0, that is infinity. Time constant is infinity, means the oscillation will take infinite time to get stable. Correct? So it means for the infinite time it is going to continuously sustain, means you'll get natural oscillation. There will be no damping. At the infinity also you'll get the same oscillations. Correct? What about this? In underdamped system, if you will calculate time constant tau, it will be minus 1 divided by the real part. Real part is minus zeta omega n, so it will be zeta omega n. And what about the natural frequency of oscillation? Natural frequency of oscillation is nothing but the imaginary part of any pole, and that is omega n. Over here it's omega n. What about this? Over here it is omega n 1 minus omega n under root of 1 minus omega n 1 minus zeta square, and that is the root. Correct? So this is, so two things we have to remember. One is the time constant and one is the frequency of oscillation. In this case, in critically damped system, if I'll talk about tau, that is the time constant, it will be 1 by omega n. I hope it's clear to you. What about omega n, frequency of oscillation? It will be over here 0, because we have only real parts. There is no imaginary part in it. So omega n is the 0. What it indicates? Oscillation. Is there any oscillation over here in the critically damped system? No, there is no oscillation. So that's why we are getting it's a 0. Now let's come to the overdamped system. Overdamped system, the tau will be, it will be 1 by zeta omega n. I'll take the dominant pole. Which one is the dominant pole? Here, the pole which is near to the imaginary axis, it's a dominant pole. So here in this case we are getting two different values on the real axis, negative real values. So which one I'll consider? I'll consider the value which is near to the imaginary axis. We call this pole is the dominant pole. Correct? So while going to calculate the time constant, always consider the dominant pole. Okay, let me write over here also, real part of dominant pole. I think it's clear to you. So in this case we'll consider this one. So this is, I'll take minus over here plus omega n zeta square minus 1. What about the frequency of oscillation? Definitely it will be 0. There is no frequency of oscillation. I hope it's clear to you. Now we'll discuss about the different values of zeta and corresponding the behavior of the system. Correct, friends? So let's come over here, and if any pole is given like this, is equal to sigma plus minus j omega n, kind of, let's take it negative. So if you are going to calculate of, or you are looking for the time constant tau, the tau you will write minus 1 divided by minus sigma, that is 1 by sigma, your time constant. If you are looking for the frequency of oscillation, it will be definitely omega n. So the imaginary part will give you frequency of oscillation. This is the frequency of oscillation. Okay, and this real part will give you the time constant. The reciprocal of this with negative sign is nothing but your time constant. I hope it's clear to you. So what I'm going to say now, please, let's take this diagram over here. I'm drawing for you. This is zeta equal to 0 condition, marginally stability. Over here we got for the underdamped system. Okay, this is the case of zeta 0 to 1. Correct. Over here we got, this is the case of zeta equal to 1, and for overdamped system we got two poles. One is near to the imaginary axis, one is away from the imaginary axis. This was the case for zeta greater than 0, zeta greater than 0. So what I was saying at the time is, when zeta is going to increase, please watch it carefully. When zeta is going to increase, or zeta is moving towards 1, from 0 it's starting, because this is the minimum value we are considering. At zeta equal to 0, our system is marginally stable. When zeta is going to move up to 1, what is going to happen? Your poles are going, see, your poles are going away from the imaginary axis and close to the real axis. See, this is your path of your poles. It exact zeta equal to 0 value, they are on the imaginary axis. Now it's going to decrease and moving to the left, also, and close to the real axis also, negative real axis. Okay, so when zeta will move like this, your poles will move left and closer to negative real axis. This is the point number 1. Point number 2 we'll discuss about. Now we'll discuss about the time constant. See, what is the time constant? The highest time constant for what? See, for undamped system there will be infinite time constant. We have seen time constant is nothing but minus 1 by real part. For the undamped system there is a 0 real part. Definitely we are getting 0. So it means the pole which is over here will contribute highest time constant. Wait a minute. Over here this is t equal to infinity. Then it's going to reduce. Over here again I'll get, see, for this also I'll get the infinity. Correct? No, for this is not infinity. For this I'll get, in this case the time constant will be 1 divided by zeta omega n minus omega n zeta square minus 1. Correct? This is for the overdamped. Then we'll get for the undamped system time constant, it will be zeta omega n, and the least time constant will be for critically damped system, and that will be omega n. Okay, so this is the highest time constant will be provided by the undamped system. Then overdamped, then underdamped, then critical. I hope it's clear to you. Okay. Now point number 3. What will happen with frequency of oscillation omega n? Omega is highest over here, so omega is going to decrease. If your pole, the condition is your zeta is moving from 0 to 1. So what will happen? Your poles will move towards the left, closer to the negative real axis. Your time constant will going to decrease, because your time constant you will get at imaginary axis infinity. Over, then you will get the overdamped system time constant, then underdamped, and the least time constant will be for the critical damped. What about the omega n? See, omega n is going to decrease. Correct? So omega n is going to decrease. Time constant, let's take it tau. Time constant is also going to decrease over here. In this case we are talking about, this is your case, okay? Please don't forget about this when your zeta is moving from 0 to 1. So omega n is going to decrease, zeta is going to decrease. What about damped oscillation? Damped oscillation, these are going to decrease. Damped oscillation is nothing but the frequency of oscillation. It's going to decrease. Over here we were getting sustained oscillation, over here damped oscillation, over here in this condition we were getting it's critically damped, over here it's critically damped, over here it's over damped. So your damping oscillation is going to decrease, okay? So your delay time or your rise time or your peak time is going to increase. Later we'll discuss about these three things, okay? So don't worry about this. What is going with relative stability? Relative stability, definitely it's going to increase. Why? Because here your system is marginally stable, over here it's unstable. So if you are moving to the left, your stability is going to increase or not? This system will be more stable than this system. This system is more stable than this. So this side, if your poles are moving towards the left, definitely your relative stability is going to increase. If your poles are moving towards the imaginary axis, means you are losing your stability, means you are moving to the marginally stability. Once you will cross the imaginary axis, you will enter in the, this is the unstable family, okay? So what is my point? If you are moving left, you are going to increase your stability. If you are moving right, you are losing your stability. I hope it's clear to you, okay? So friend, this is all about this zeta analysis. Now this all thing we were discussing about the impulse, if you remember, I considered second order system. If you remember this second order system, I gave del t, that is the impulse, unit impulse, okay? I got some output, okay? This output or this two relation between input and output is affected by your zeta value, external, okay? Now your CT, we got 4 values for del t, and those 4 values are for zeta equal to 0, for zeta is in between 0 to 1, for zeta is 1, for zeta greater than 1. Means for a particular input we got 4 outputs, because your output is controlled by zeta, okay? Similarly we'll apply to this system your unit step, then you'll get 4 output. You'll apply your unit ramp also, you'll get 4 output. You'll apply your parabola, you'll get 4 outputs. So till now we discussed these 4 outputs for unit impulse, correct? Now only one is important for if we are going to discuss about the unit step. Unit step output is important in this region only. Which one? This region 0 to 1. Means now our next task we will not going to discuss all these 4 conditions for unit step also. For unit step only we'll take this case. This is the second order system. We'll give this UT. We'll get output CT, and this CT we are going to discuss only in underdamped this range. For the value of zeta between 0 to 1 only we'll discuss about this. This one is very important, okay? So we are going to discuss about this only. So let's start it. Friends, if you will apply the unit step, what is the transfer function? The transfer function of the second order system is nothing but omega n square divided by s square plus 2 del omega. This is zeta, okay? Sometime I call it del. So 2 zeta omega n s plus omega n square, correct friend? So here Rs will be 1 by S. Let me change the pen color. 1 by S, and you will get the CS value. That CS value we are going to discuss in the range of 0 to 1 for underdamped system only. For underdamped system only. Okay, so when you will solve this, you will get, this is the very important formula. Okay, and the formula for the output for unit step in this range, and this formula is 1 minus e to the power minus zeta omega nt divided by 1 minus zeta square. Over here it's sine omega dt plus phi. Correct, friends? Where your omega d, you know very well, this is omega n 1 minus zeta square. Correct? What about your phi? Your phi is your phi is nothing but cos inverse zeta. Okay, so this is your system response for the unit impulse in the range of 0 to 1. This one is very important. Okay, so this is too much theory in this chapter. Soon I'll start the problems, don't worry about that. Okay, let me cover it first. So what will be the response nature? We already discussed about this, but again I'll draw the waveform. Your oscillations will be, let's take this is the desired value 1. Okay, this is 0. Over here your system is going to start, it's going to oscillate, and at the time will pass, your oscillation will die out. So this will be the response of the system. This is your CT, whatever we got over here, this is nothing but my response. Correct? Okay, so friends, earlier I told you that we are using this system only. Okay, why? Let's discuss about this. Okay, see, if your system input is unit impulse is your input. What about the transient behavior of input? That is the unit impulse. Yes, we do have the transient behavior. But what about the steady state? No, we don't have, because at the steady state your input is not present. Your input is defined for t equal to 0 only. Correct? So what about the stability? So practically stability is not exist for this. Correct? Now if you'll talk about the ramp function, that is RT, for the RT, transient behavior will be there for the system. Yes, definitely. What about the stability? Yes, stability will be there, but what about the steady state? Steady state will be there, but stability, no, this is not stable system. See, this is unbounded, right? RT is nothing but T. T is nothing but, here is the graph. This is unbounded system, not a stable system. Same thing will be there for the parabola also. Yes, we do have the transient and steady state behavior of the system, but this system are not stable. So what we want, if you are going to design the control system, it should be stable or not, and it should provide the transient and steady state behavior. Correct? So over here I'll take the unit step. Now unit step is, yes, we'll be having transient behavior or transient response, steady state response also, and the system is stable. Okay, that's why we are using this. And under which reason we are using this, or which range? Zeta range 0 to 1. Okay, this is the perfect range in which we can design any control system. Correct? So friends, this is all about this class. In the next class we'll finish this. We'll discuss about the time domain specifications, and then we'll finish the theory part related to this, Then we'll switch to the problems. I had to cover so many gate problems, so it will be crystal clear to you people. Then I'll come to the steady state error. Steady state error is another important parameter of this unit. Then we'll finish this entire unit. Okay, so friends, we'll meet in the next one. For the you can subscribe the LGF. For the more update, you can press the bell icon, and you can join on the Facebook, so you can ask any doubt. You'll get your answer there. Okay, we'll meet in the next lecture. Till then, take care and bye.